Hi everyone, my name is Eugene here, and today our group KL will be presenting to you our group study on the real life case related to static. Throughout the video, this will be the learning outcomes. In our study as well, we will be using laws of force and moment to solve our problem. This is important to identify all the forces so that the resultant force calculated is always zero to keep a structure in equilibrium. A structure is in equilibrium when all the forces or moment acting upon it are balanced. In the video as well, we will be using moment of inertia in our study. Moment of inertia, which is also known as the angular mass, is the quantity that determines the torque needed for a desired angular acceleration about a rotational axis. Moment of inertia help us to understand the resistance of a body or a structure towards the changes in its motion. This will be a real-life structure our group have chosen for our study. This is a hut in a garden.
Now, I'm going to explain about free body diagram. So, what is a free body diagram? It is known as a diagram that shows all the external forces and also torques which are acting on the object. So let's check it out.
Take a look at the body diagram below. The body is in equilibrium, or in other words, it is not moving. In fact, it is held static by the ground. Now, look at the applied forces on the body. First, we can see there is a 55 Newton force exerted on top of the hut. Not just that, there are other two identical vertical forces exerted downwards on the middle beam of the body. Therefore, the ground must exert vertical force upward in order to prevent these downward motions. Next, let's look at the base of the body. Two identical types of connection can be seen, which are identified as rockers. As we all know, connections such as rockers and rollers, the forces are always perpendicular to the surface.
Forces and moments. Forces are in equilibrium means that the resultant force in all directions are zero. When the forces acting on an object are balanced, they cancel each other out. The net force is zero. The conditions for equilibrium are the sum of all forces must be zero, Fx and Fy, and the sum of all torques or moments must be zero. So this is the free body diagram of the hut, and below is the condition to make it in equilibrium.
Okay, as Ilman stated just now, the forces must be in equilibrium in order for it to be static, and so must the moments. So in this case, we fix the point at A and we calculate the moment around A, and using that we find what is the force that is acting on B. And then we fix the moment on B and we find what is the force acting on A. Then we sum up the forces to check whether our calculations are correct, and the sum of the total forces is equal to zero, so it confirms that the structure is in equilibrium.
And now I am going to calculate with you the moment of inertia of this hut. So, the formula that we're going to use to calculate all these beams will be the formula of integration of y square delta E, where delta E will be the x component dy. So by using this formula and substituting the value of the y-axis, we will get the moment for AX and CX, that is 2.9418 m power of 4, while BX, using the same formula as stated above, is the moment of BX will be 0.4458 m power of 4. Moment of D and G, DX and GX will be 1.1257 meter power of 4. Next will be the moment of EX. the moment of Ex will be 3.083 m power of 4. Next, we will gonna calculate the Fx, moment of inertia that stated after applying the same formula here will be 0.7367. Moving on to Mx and Nx. Due to this being an irregular shape, our team decided to cut it into two shapes, which is two parts, which is one here and the other one is here. So this is Mx, and the moment of inertia at Mx will be 0.0643 m power of 4. Next will be Jx. Jx is located here. As you can see, this part of the hut is like an arrow, but to ease the calculation process, we decided to break it up to J and F. So the moment of inertia at J between 3.657 and 3.634 will be 0.02. Next will be H and I. The moment of inertia at H and I will be 0.4655 m power of 4. Last but not least, the moment at K and L. Kx and Lx will have the moment inertia of 0.1706 respectively. So, after calculating each and every one of the moments here, the beams, we need to sum it up. So the total moment of inertia will be the summation of every beam respectively and results into 13.8213 m power of 4. Thank you.
Alright, as we can see here, I've divided several parts to make it easier for me to calculate the moment of inertia. I've divided it into parts A, B, C, D, all the way to parts N. And also made several equations to help me with calculating the moment of inertia, such as y1, y2, y3, y4, y5 and y6. Now, how do we calculate the moment of inertia of the hut shown here? Let's say we want to calculate the moment of inertia at A. So obviously we use the formula integration x squared dA. Now, how do we determine from where we integrate? And since the varying variable is dA, but the unknown here is x, we need to change the dA into delta x for it to be able to integrate, obviously. Now let's go back. As we can see here, if we want to integrate the moment of inertia of the y-axis, we create an imaginary strip which goes along the y-axis at A. Now, from the strip shown here, we know that the variable that is always changing is the x, and we can show that it's changing by putting the letter delta x here, and the constant, which is ever so constant, is the length, the height actually of the block A here, which is 3.174, all the way from the top here to the rocker below. And from there we can input it into the formula, where we know that the delta A is equivalent to 3.174 times the delta x, we get the delta A, and when we substitute it, we get this here, 3.174 integrated from 0 to 0.276, because we want to find the integration from this point here to this point here, which has the length of 0.276, because the frame of reference starts from here, which is 0, so to here is 0.276. Now, as we have inputted into the formula of the integral, we get the answer 0.0222 m to the power of 4 moment inertia of the block A. Now, it's all repetitive until n, and from there we will get the total moment of inertia by adding all of its of all its what? Constituent parts, yes. By adding all of its constituent parts, we will get the total moment of inertia, which is 31.101 meter to the power of 4, yeah.
For conclusion, a free body diagram helps us to give a clear image of how forces are involved on the structure with their direction and also magnitude displayed. Secondly, by using the laws of force and moment, we know that all the forces are balanced. The external forces acting upon the structure is always cancelled out by the reaction that acts on the support of the heart, which is the rocker, so that the resultant force is always zero. Thirdly, the moment of inertia tells us the moment required in order to change a state of an object or a structure from rest to start a motion or vice versa. Thank you.